You can talk now. This is a safe space. Yes. Yes. Overfitting. Yes. Our job is not to throw the most shit at the wall. Our job is to get the model to learn. What does learning mean in this context? Supervised learning means out of sample performance. We're always thinking out of sample. We're always thinking, what could have happened if I had a new set of observations be generated? And if we're frequentists, we're going to do what would happen if I had 1,000 different data sets that could be generated again, theoretically. Okay, so we put that hat on. Okay, and now we see, okay, fine. We've got this prediction machine. How do we fix this problem? Well, as it turns out, in order to get the learning part of this process to work, which is the important part, not the model class that you're working with. So this, what I'm going to teach you now, applies in general to all models. The important part is managing the complexity of the model. Okay, and that we do via regularization and validation. Okay, so validation and the learning problem is very closely tied. Okay. Now, as we have it, the actual learning problem, defining it mathematically, is a bit of a difficult problem. The machine learning has its origins in a sort of mathematical approach to classification, essentially. This was developed in the 70s by Vladimir Vapnik and friends, mostly him on his own, and then people on the other side of the planet. And then many years went by. A lot of the stuff that Vapnik did was kept behind closed doors because he was sitting in Russia, and Russia was going to Russia. But many years later, these Americans, they dig up this guy's work and they say, okay, cool, well, now we've got a mathematical paradigm for learning. This is very interesting. And this was essentially the set theory, and which would in the modern days be called model theory. But it defines learning in a very narrow sense. Fortunately, where we are now, we've sort of relaxed a bit of the formalism because we see that really the only practical way to do these things is not to work out mathematically what is the out-of-sample performance of your model. Indeed, that becomes very difficult. You'll learn all about that in the master's machine learning course when we talk about dichotomies and things like that. But what we do nowadays is more practical. We manage complexity by way of regularization. Okay. What we mean by learning is still in the very narrow sense of perform out of sample. That's it, essentially. Okay. Now, as it turns out, we can manage the complexity of the models that we have on a more or less continuous scale. So what we did in our last lecture, we were saying one network is the simplest, a 25 network is something complex. We can pick a discrete value somewhere in between, but that's not actually what we're going to do. Like last time I said, we're going to set M to like 25 or 10, so we say a base level of complexity is at least this. So your machine can generate very general patterns. And now we're going to go back to our machine. Think of our machine as having levers that you can pull, and we're going to put constraints on those levers so that the set of patterns that we can generate becomes smaller and smaller and smaller, and hence the model complexity becomes smaller. Okay. Now, we want our model to be sufficiently complex to extract the underlying pattern. But again, what we can extract is a function of the sample dynamics. Okay, how many observations we have, what the signal-to-noise ratio is, roughly how much noise is there in your data. Okay, and we want our model to be complex enough to extract the underlying pattern, but we also don't want it to be so complex as to simply recall the observations that it's seen. Because what we mean by learning is to be able to perform out of sample, so on new observations do predictions. And that usually corresponds to bashing down your model a bit with regularization until it produces a simpler pattern or set of patterns. Okay. So yeah, indeed, how it works in the world of machine learning is any claim that a particular model is a valid representation of the data must be accompanied by a so-called validation analysis, which ensures that your model generalizes to unseen observations. So I cannot stress this enough. All the work that you do with these machine learning models, none of it matters if you don't show the validation analysis. If you don't show the validation analysis, the person reading your paper or your report or whatever must assume that this model has not learned. Okay, so if you can't show me your validation plot, I don't care what machine or what tool, how much server time or how many millions of dollars you spend, if you can't show me the validation analysis, you haven't demonstrated that your model has generalized under the learning paradigm that we have. Okay, so this is very important. Okay, so we already know this is really simple actually. If our model is too complex, we're going to overfit. If it's too simple, it's going to underfit. We need to find a trade-off. Okay, and if a good balance is found, we can rightly replicate the true underlying pattern in the data, or at least something which approximates it. Okay, and that is the learning part. Now you will have done this already. A sort of formal approach to this would have been the bias variance decomposition. Okay, so can anybody explain to me what that is? So I used to just explain this, but now you've done this in part A, now you're going to explain that to me. So as a group, you're allowed to take one punch each, and I shall take it. Come on, who wants to give it a go? You want to give it a go?
Yeah, I can try.
Okay.
So basically, what we're saying is that for every model, we will always have an issue with our variance and our bias. So we try to kind of like stabilize both of them such that both are at their minimum. So what we're doing there is that we are saying that when we have our output will definitely have the predicted, and then we subtract the actual value, wherein now we take its expectation, which its expectation can be divided into the model variance, the model bias, and also the noise. And we try to minimize we try to minimize the two variance and
trade-off between the two.
Yes.
Cool. So sorry, you give it a go. I saw your hand was up. Come on.
Yeah, it's basically, yeah. It's, I think it's the noise the irreducible.
Yes, noise. There's some component which you can't get around.
Yeah, and then the bias and variance is sort of the reducible error. And
Yep,
then
so-
you try and minimize it.
Okay, you try to minimize. Okay, but so what is the dynamics between bias and variance?
As variance, like they inversely, like they have an inverse relationship.
Inverse relationship. Okay, can someone explain that? Yes.
That component, or can I?
Yeah, you can just go for it.
So, from my thinking, it's as you overfit your model, the bias increases and variance decreases. If you underfit it, then you have a high variability and a low bias. So it's all about finding the best set of parameters that captures the underlying trend, because as was stated, there is some underlying trend, but there's also the accompanying noise that we can't account for.
Yeah.
So it's kind of finding a balance.
Yeah. So there's like three things going on. You wanted to give it a go?
Yeah, I was just going to add on to that, like talking about your variance. Essentially, you'll be talking about your training set and your bias, your out of time set or your validation set, because the bias will be indicated when you look at your out of time data set. As your variance, you look at your training set to minimize the variance there.
Okay. So here's how I think of it. So we always think in terms of out of sample performance, right? So we want to figure out what is the out of sample performance of the model that we've selected. So G, a model G selected from some data set that we've taken. Okay, so we want to then, that's selected in sample, we want to see how it performs out of sample. Now, on the out of sample, there could be many realizations out of sample, all right? So we need to figure out, well, what do we expect to see out of sample? That's where this expectation comes on. So over all possible data sets generated out of sample, how does this thing perform? Okay, So we want to minimize that, obviously, right? Because our definition of learning is perform out of sample. Very simple, very narrow. So we want to minimize this quantity. Okay, so now we say, how do we do this? Well, we're clever mathematicians. We're going to set up a data generating process. So we set up a mathematical model for how the data were generated. So we start off with an equation that looks like that. We say that the inputs come from some joint distribution. We've got some noise in the data, some error distribution. And now we're going to decompose this thing into various components. Okay. Now forget the expectations for a second. I just want you to look at the specific components. So G, again, the model selected from a data set in sample. Okay. Evaluated at some point in the input space. Let's compare that to the average model fitted at that point. So what is the average model fitted at that point? That is the average model fitted over all possible data sets. Okay? Let's see how far they are apart. So square that distance. Okay, and then integrate that. What do I mean by integrate? Well, we integrate over all possible data sets. So we integrate over all possible data sets. What does that tell us? It tells us something about the variance. This is literally the expression for variance. That's a mean, that's a variable, and this is an expectation. And now this outer expectation over x is saying, well, let's not only check what the variance is at each point, let's add up all those variances at all of the points in the input space. That's what this first term is doing. So this is calculating model variance. Okay, now, if our model is very complex, right, what will happen? As each data set changes, what's the pattern going to do generated by our model that's fitted? Our pattern's going to match every data set. So think about a noisy data set. How noisy is the model fit going to be? As noisy as the data, right? So if you've got a complex model, it's just going to replicate your data, and your model's going to vary a hell of a lot. For each sample, it's going to produce a different pattern. So variance goes up as model complexity goes up. That's bad. We want to get that to go lower, right? So we might want to select a model which is simpler, so we can lower the variance. Okay, now, where's the trade-off come from that? Okay, let's now compare the average model fitted over all data sets, so that's G bar, to the true underlying pattern. So this is the thing that we want to extract. So we want to see how far is the average model for a given complexity from the true underlying pattern, square the distance and integrate that. If our model overfits, right, in sample, that's bad for variance. But on average, what will happen at each point, the models will pass through the exact true underlying pattern. So this thing will be small. Okay, so now we go back and we say, oh, that's not good, this thing is going to be large, so let's dumb down our model. If we dumb down our model, on average, what's going to happen? It's not going to change a lot over data sets, so we're not going to have lots of variance, but what's going to happen? On average, this thing is going to be far away from the true underlying pattern, so the bias grows. So there's a trade-off. One goes down, that means the other one goes up. But because we're adding them together, we need to find a balance in the complexity. And as always, there's a noise floor. This is the noise floor. This is the thing that you cannot get around. And this is what, in general, makes using machine learning algorithms for problems, just making that the first thing you throw at a problem, a bad idea. Because lots of problems have a very high noise floor. And then it's a bad idea to use these unstructured machine learning models where you cannot see where things are going wrong. Okay, in that case, if you have lots of noise, so poor signal to noise ratio, then you want to use a simple model, which may not predict as well, but when something goes wrong, it'll be robust. Okay, fine. So that's the bias variance trade-off. What is the problem with the bias variance decomposition. Can anybody spot the problem? So if we want to use this decomposition to choose a model. Come on, give it a go, yes.
Well, it assumes that you already know what the actual form is.
Yes, it assumes that you have F. You cannot evaluate the bias if you don't know what F is. Okay, now, this is very interesting in the master's machine learning course. We do these calculations by way of simulation, and yeah, we do lots of interesting experiments. There's this one simulation experiment which always takes the students a couple of weeks to figure out. And they always come back and they say, this is impossible. And then I show them a picture and I tell them this was done on my shitty computer that's not even in my office anymore because it can't even run Windows 10. And then within a week they would have solved it because now all of a sudden you can figure it out. But what that picture essentially tells you is in general what you should know about bias. But yes, you're right. We don't know what F is. Moreover, we don't know what the true data generating process is. So we get clever. We say, fine, we're not going to do this decomposition. We're going to focus on the left-hand side. Okay. So, sorry, this is just a plot demonstrating in a simple model versus a complex model. So on the left-hand side, so I'm simulating data sets. Blue is the true pattern. This dotted line is the fitted. And this is going to be a simple linear regression. So can you see this model? It's pretty stable over all data sets. Here we fitted, what was it, a fifth order polynomial to the same data set. Can you see that the observations, right, the model typically passes through the observations, so we get perfect fit in sample. Okay, do we extract the underlying pattern? No. And what else? Model varies a hell of a lot, as much as the data varies. Okay, and what are those components doing the bias variance decomposition? It's always looking, how far is this line from the true? How far is that line from the true? And integrating that. Okay. Cool, and in general, this is a decomposition. This is another thing that we do in the master's machine learning. You shouldn't worry too much about this. This is just to sort of explain what we do. Okay, we shift our focus to the left-hand side of that equation, and we do the following. We do a validation analysis. So validation analysis is what? We take our observations, because that's all we have. That's the information we have. We've got a model, we've got some data, and that's it. We don't know what the true data generating process looks like. We're probably not going to have a mechanism to generate multiple data sets, that kind of thing. So we play pretend. We say, let's pretend half of the observations is in-sample observations, and then another half is maybe a new data set that was generated. Okay, so we create a training set, and then a so-called validation set. Okay. Now there's actually a third data set that we set aside. Okay. So there's a training set, a validation set, and then a test set. Okay. The point of the validation set is to fit our model in sample on the training data set, and then on the validation set, check how our model is doing on unseen observations. And then we're going to change the complexity. We're going to have some mechanism that we can change the complexity, right? So just a single thing that we can change to manage the complexity of our model, and then we're going to see how it performs on the validation set. Okay. But we also keep aside this test set. Okay. And yeah, this validation set is the mechanism by which we show that learning is occurring. So, can you see what we're doing? We're trying to evaluate or approximate this side of the equation. We're trying to minimize that, manage the complexity, and we're going to do it in terms of the validation set. And our proxy for the out-of-sample data is our validation set. Okay. Now, important. Why do we keep a test set and a validation set? Yes, Max.
Because even though you're only glancing at the validation set, you're still optimizing based on that validation set. So you still the observation and the validation set is still somewhat seen by the model because you're training your hyperparameters on them or something else on them. So you need a set, i.e. the test set, to see how it truly performs on truly unseen data which have absolutely nothing trained on it.
100% perfect. Yes. The validation set, this is our play pretend data set for the out of sample data. But we measure the performance of our model on that validation set. So yes, we are training in sample, but the complexity parameter does effectively a pattern or a model selection. So again, if we think about our machine learning models as something that generates, this machine can generate this set of patterns. Set of patterns is that big. We're going to bash it down with regularization so that the set of patterns becomes smaller. And then when we do the training, we select one pattern from that smaller set. Okay. Now, that making of the set smaller is influenced by the regularization parameter. That regularization parameter is determined by the validation set, which means that information in the validation set ends up in our model. So, a validation set is not a test set. A validation set is always going to be optimistic in terms of performance. Okay, now it's interesting to note that validation and the validation set is essentially an unbiased estimate. You can go and show that. That's what this equation says. The expected out of sample performance, if you use a validation set, is the expected out of sample performance. But that's different to, you can match something in expectation, but the distribution of that thing might not be symmetric. And that's what this picture is saying. It's saying that we've got a validation set size, it's got a distribution attached to it. The expected out of sample performance is that as a function of the proportion of data that we use, and those two things are the same. But effectively what happens is you're more likely to perform well on the validation set, simply because you've used the information in that validation set to pick your model. Okay, so, yes?
How do you decide on how big to make your test set? Because you obviously want to use as much of it as possible in the training of the model so that your model gets as much of the pattern into the actual model, but then you don't want to have too much variability in your test set and then integrate your model.
Excellent observation. We have to choose what proportion because we only have so many observations. Okay, now the test set. The test set is something we hide underneath our bed, we don't look at it. That's the very last thing we need to look at because we need to keep its sanctity. The model must never get to that data until they're right at the very end when we need to make a decision. Okay. Now yes, the validation set itself, so when let's say we've put a set aside the test set, we want that to be big so that we can get a good selection criteria, I guess. But the same applies essentially to the validation set. We want to have as many training observations as possible so that we can get the best possible estimate for the parameters of our model. We also want the validation set to be as large as possible so we can get the best estimate, right? This estimator, this thing. We want as many observations in the validation set as possible so that this thing is as stable as possible. We can get a good validation error estimate. But we only have so many observations. The answer to your question is to figure out what is the ideal proportion, what is the ideal ratio, and that's what this experiment does. We do this in masters. You take a proportion and set it aside as a validation set, you fit a model, and then you check how much the true out of sample performance varies. And here you can see, if you set the size of the validation set small, what happens? You get an estimate that's on average at the point because it's unbiased, but the variance is large. So you're only going to have a single realization. How do you know where you are on this curve? You don't. And you're more likely, I guess, to be in an unfavorable position. As you increase the proportion of the validation set size, you get a better estimate, more stable estimate. But then at some point, what happens? Your model performance goes down, so the expected out of sample error goes up. Why? Because you get a poorer estimate out for the model parameters. So your model starts performing poorly, just overall. So the conventional wisdom is you should use like maybe an 80-20 split, so 80% for your observations in sample, 20% for validation, and then you keep the test set aside, that kind of thing. Tenfold cross-validation is more like 90-10%. Best true estimate you can get is a 50-50 split, but then you want lots of observations in both sets. So it really is situation dependent. In an exam, what I will do is I will tell you what the split should be. Okay, cool. But yeah, very important question, and it really is situation dependent.
Would it be considered okay to, let's say, you have your split, you test your multiple models on the training set, validate them on the validation set, and that's done. Now you take your best model based on the validation sets, and then take that, what you've learned from that, and now fit a model using that information to the entire set, and then test.
Yes, well that is something that you have to do. So right at the end, so we'll talk about that in detail, right at the end when you want to fit your final model, you put the validation data back with the in-sample data. That's so that you maximize the data set size, but then you've already selected the complexity level. There's a bit of a jump there, because you're assuming that after you've put the data back, that the level of complexity that you've chosen is correct. It's a bit of a leap of faith there.
But we're also making that same assumption for the test set as well.
Yes, this is true, but we know that there's a difference, right? So, and just be careful when you're talking about, so for each one of the models that you would fit, so let's say you had different machine learning algorithms that you were fitting, you would do the validation analysis separately, and after you've selected, put all the data together, fit them, and now you have your candidate models, and then you go to your test set, you check once, and then you go home. Because the moment you go back now and you change something to see if it performs better for a second time on the test set, what has happened? Your test set is no longer a test set, it's now become a validation set. Yes, there was a hand. It was yours, yes.
Is it kind of like illegal to put the validation set back in? Aren't you then like almost like biasing it towards validation set? Because you already chose quite a lot of information from it because you chose your like model complexity based on that. Is it just because you need more data? Like,
You want to maximize the amount of information that you select for the parameter, or that you use for selecting the parameter.
It's still like worth it.
It is, yeah, it is. So you, yes.
When you do a cross-validation analysis, you select, you take one big training set, you break it into little chunks which you call a validation set each time. I understand in the case we use the validation set separately, because then you completely hold it out, it's not trained on, but then when you're taking these individual validation sets over these chunks, actually even though like you are doing it multiple times, the selection and the crossover of the set would have some biases.
Yes, so what your colleague is referring to is when you do the cross-validation, there's some overlap in the sets that you create. Okay, so when you're comparing the model performances, what are you're comparing correlated things. As it turns out, when you calculate the average of those, you're fine. It's when you calculate the variation of those that you have a problem. Because they are correlated, what will happen is you'll underestimate the variation in that. Now, I'll come back to the variance of the validation error. Let's draw the validation curve first, and then I'll talk about that. Just remind me if I don't. Okay, fine. Cool. So, how do we do this practically? Well, we do this by regularization. So regularization is essentially a technique for applying the brakes on complexity. Okay, so remember, we've got some objective function, so let's say we've got some mean squared error. We've got our model sits in here. We start up with something which is complicated. And if it's complicated enough, we can get these predictions to match these observations exactly. So this objective we can minimize exactly. We can make this 0 if we've got enough parameter and time and compute. We know now that's not good. How do we manage the complexity for our model? Well, this is why I like to think again of our neural networks as little machines, and each of the parameters in that model is a little lever that we can pull on our machine to generate a pattern. So what we do is we say, well, let's constrain how far you can move those levers. So you can take the lever from all the way down here, you can take it all the way up there. So if you had 31 parameter model, for each one of those you can move it as far as you like. Now I say, well, hang on, you've got a budget for how far you can move the levers. And how we do that budget is you take the sum of the squares of how far you've moved that lever, and the sum of all of those squares must be less than some threshold, let's call it tau. So can you see if I make that budget small, you're not going to have lots of leeway to move, which means what? You're not going to be able to generate many patterns. So can you see how that constrains the set of patterns that you can generate? If I make the budget infinite, then you can move it as far as you want to. So infinite budget means I can get these predictions as close to that as possible. If I make a small budget, you're going to have to find a compromise which gets this as close as possible to that, but it's probably not going to be 0. Okay, so we add this budget constraint effectively. So we constrain the model, and how we do that for neural networks is we take the sum of the squares of the weights in the model. So there's no biases in there. We leave the biases untouched. Yes? Or you're asking a question? Yeah?
This is obviously one method, but multi-normal. Then you've got L1 norm, which is absolute. And then I think Corey mentioned it the other day, but this dropout. How would dropout, I understand that you're setting certain ones to 0 when you pass it through, but how would that work in a neural network? Because I know it's used in neural networks, but mathematically,
So it's literally setting some of these at random 0, okay, and then for each one of those models, the sum of the squares would essentially be a constraint. But that's more like of a beforehand saying the pattern, the set of patterns that we can generate is going to be small because all the subnetworks for which we've set the parameters to ignore, they imply smaller sets of patterns. And then essentially for dropout, it's just an ensemble of those simpler models. But it is still regularization. Okay. Cool. So we take the sum of the squares of the weights, and we leave the biases untouched. Okay. Quick question. Why do we only constrain the weights and not the biases? We want to give it a go.
It's similar to why we don't really consider like p-value for linear regression and stuff. I mean the intercept term. That's it.
Okay. So yeah, I think that the easiest way to understand what this is. So remember with the perceptron, we were talking about we have these planes that we can rotate. Now, in this neural network, we also have these little equations for planes, and you can sort of think of the pattern being generated as a function of how these planes can be moved. Now, constraining the W's is the sort of orientation for those planes. What is the bias term doing? In the response, it's dimension, it's moving it up and down. So you don't want to constrain the up and down, you want to constrain the orientation of the plane. Okay. So you have to leave the biases unconstrained. Right, now, it turns out, constrained optimization. Have you guys done constrained optimization? Okay, constrained optimization, difficult to do. But, as it turns out, for the simple constraint that we've set up, it's not difficult to transform the problem into an unconstrained optimization. So what do I mean by constrained optimization? Constrained optimization, optimize this objective subject to that set of constraints. Unconstrained optimization is, I give you an objective and you just have to optimize it. There's no constraint. So we take that problem, we turn it into an unconstrained optimization problem by noticing that for that constraint, there's a corresponding Lagrangian parameter So we can take our original objective plus some, I guess, regularization mechanism multiplied by this new parameter. This new parameter is essentially the Lagrangian for the constraint. So that new parameter and that budget tau are inversely related. Okay? So if nu is small, that means the budget is infinite. If nu is large, the budget is small. So tau is small. Okay, you can see that by if nu is 0, we just have the unconstrained original objective and we overfit it. If we add this constraint, we make nu greater. What do we do? We are simplifying our model. So this thing is the brakes on complexity, literally that parameter. And this is what's clever about it. We're going to choose that parameter beforehand. We're not going to figure out what is the Lagrangian for the optimization problem. We're going to pick it. And we're going to pick it in a way such that we get the best out of Toml performance. So we fix this parameter, and then we solve the unconstrained optimization problem, albeit at the hand of what I like to call a modified or a penalized objective. So you have objective function plus penalty is penalized objective. Okay. Now we have lots of forms of constraint that we could apply. In general, we have the P norm. So for P equals 1, we get the absolute values essentially of the weights. Okay, so that's L1 norm. Yes, you were referring to. The other one's Tikhonov regularization. So this is essentially an ellipse. Okay, yes?
When you say we pick up a form, do we perform a validation analysis to select it?
We perform a validation analysis to select it, but every time we optimize that objective, we fixed new. So we fix new, optimize, fix new, optimize, fix new,
We're not
optimize.
optimizing based on it.
Yes, based on a fixed new, based on a fixed level of complexity essentially that we've chosen. You'll see how it works when we go. Okay, we've got dropout regularization, which essentially says at random with some probability, set the weight equals to 0, so we've talked about that. This is something you don't have to worry about. This is just something you'll see in code on. There's a bit more to it, but read some papers about that. Early stopping, complete garbage. Don't do it. This is when you're lazy and you don't know what you're doing. You do early stopping. Okay. You can fight me after the lecture if you want to about that. Okay. So how does this work? So here's a demonstration. This is the true pattern in the data. Those are our observations. Okay. And we're fitting like, I think it's a 10th order polynomial. Okay. And as we start out with a low value of nu, you'll see that we had a very complicated model passing almost through all of the observations. And then we'll ramp up the new parameter, which constrains the model. And what can you see? As we start constraining the model, what happens? The pattern becomes simpler. So this pattern here is a 10th order polynomial. Does it look like a 10th order polynomial? No, it looks like something a lot simpler, right? It almost looks linear. And indeed, if you constrain the model far enough, what happens? It literally becomes the simplest model you could have. What is the simplest model you could have?
Intercept.
An interceptor, which is a flat line. So we could have a 5 million parameter model because we've left the biases unconstrained. Okay. Once we do regularization, if we regularize it far enough, it is equivalent to an interceptor, a 1 parameter model. So what is the effect of changing this new parameter? We're essentially, by changing nu, managing the complexity of the model, we're changing the effective number of parameters in our model. So we might start out with a model which has 140, 70 or whatever parameters for our 50 data points. But by the time we've constrained it a bit, we have effectively a model which maybe has 3 or 4 parameters. So can you see now what my argument is about? Don't try and throw as much shit as you can at the wall and try and figure out how many nodes you have, that kind of thing. Start with a model that has enough nodes and parameter and freedom, and then bash it down with regularization until you get to the appropriate level of complexity. Okay, so that is the effect of regularization, and that's how we're going to manage complexity. Just a technical note on, well, which form of regularization should you use? Now, so which form of regularization should you use? Okay, this is easy to understand if you consider what we're doing. So back when I showed you this, I was showing you an objective function and a constraint. This picture on the left-hand side, this surface, that's the objective function. And for this problem, we're pretending we've got two parameters in our model. So not the intercept, so we just have two parameters in our model. That's the objective function that we want to minimize. The minimum of that surface is that dot over there. So we want to get to that dot. We then set a constraint, okay, and that constraint is the sum of the parameters squared must be less than some threshold. What is the sum of those squared parameters? If you've got two parameters, that is a circle. So in the parameter space, I'm constraining you to a circular region. And I'm saying, get as close as possible to this dot, but stay within this circle. And which point is that? That's this blue dot over here. Okay. Well, you can see, as I'm changing the constraint, I'm changing how far you are from that optimal. Okay. And, okay, how are we doing that? This is the constrained optimization problem. I said we find this solution by figuring out a corresponding unconstrained optimization problem. Right. And that's the surface on the right-hand side. This is the unconstrained problem. So this is the penalized objective function. And what can you see? Here the surface is changing such that its minimum is the blue dot. So this blue dot, which is the minimum of this surface, corresponds to that solution. Those two things are equivalent. So we set up an equivalent unconstrained problem. Okay. Now, what penalization term you use affects the parameters of your model in different ways. For L2, what can you see is happening? So remember, these are now the axes for your parameters. What's happening to the parameters? So when you do L2, I'm sure you've done this in the first section of this course. What's happening to the parameters? They're moving towards where? Zero, the origin. Okay, so the parameters are shrinking. Okay, are you guys, you're doing Bayes, right? Have you done shrinkage? So you're not at the likelihood inference bit yet. Okay, so you'll be pleased to know that there's a Bayesian interpretation of what we're doing. And the Bayesian interpretation is this. We're putting a prior for L2 that these weight parameters are all normal with the same variance. That is effectively exactly the same thing that we're doing. Okay. Now, this is just another way of demonstrating the figure there. So we've got the original objective function and the modified objective function. What are we doing? We're changing the shape of that surface as a function of nu, the regularization parameter. And what can you see? You're changing the problem into something which is ever more convex. Okay. So that's another thing to keep in mind when you're doing regularization. When you're changing the objective surface, you're changing the nature of the optimization problem that you solve. The more convex this thing, the better. Okay. So the easier it is to solve. And in general, you'll find that your algorithms find these solutions quicker. Okay, what about the L1? Okay, so now we say, let's change the budget calculation. The budget calculation is take the absolute values of the parameters. Okay, so we've got our original objective surface, that's this thing again. Our budget calculation is now this diamond-shaped thing, and now I'm telling you, find the solution closest to that within this strange budget calculation. Okay, again, there is a corresponding unconstrained objective or penalized objective function. And what do we see happen to the parameters? Yes, hand at the back. Some of them get set exactly to 0. So can you see that this parameter, beta 1, hits 0 there, and then it shrinks, and then the other one gets set to 0. So what is this doing? L1 is effectively setting the parameters, some of the parameters in 0 to 0. And there's in fact a sequence in which it will set the parameters to 0. Okay, so when you were doing the lasso, you guys remember that? That's exactly the same thing. Okay. Now we can apply this to neural networks as well. And we can set some of the parameters on our neural network to 0 as well using L1 regularization. Okay. So again, if you were intent to set some of the parameters in your network to 0, I would argue that this is probably a better way to do it than dropout. The only benefit you get from dropout is the ensemble nature of the models that you fit. But this is probably computationally more efficient and easier to do the validation and analysis for. Okay, because you can order the complexity of the model. Now, there is a problem with L1 regularization. I'm actually not allowed to answer. Who's going to tell me what the problem is with L1 regularization? Yes, sir.
Correlated variables.
Okay, so I'm not so worried about the inputs at this stage. What is the problem with L1? Yes.
Non-differentiable.
Non-differentiable. Yes. So when we calculate this objective, is this thing differentiable? No. Okay. And where does this thing go? It goes in the modified objective function. It goes here, right? So if we want to take we want to differentiate this function with respect to any of the weight parameters, what do? We're industrious machine learners and we bullshit our way to an approximate gradient. I'll show you how that actually works. But yeah, you can sort of see the problem arise in this objective surface, the unmodified. Look at the contours of this objective surface, how it's changing. So here you get a sort of smooth change. It just stays a little ellipse and it gets smaller and smaller and smaller. Okay? What's happening there? You get this ellipse and then it becomes this sort of weird egg shape. Okay? What's happening there? So in this next picture, when you compare, so this was the old surface and this blue surface is the modified objective function. What can you see happen in this surface? You get these creases around the axes. So what's happening to the objective function? The objective function is folding around the axes. Okay, now why is that a problem? Because remember, this is the thing that we're optimizing. So along some of the dimensions, what's happening? The objective function is folded around that axis. So your numerical procedure, how is it going to find the minimum? It's going to be unstable. Okay, so L1 regularization, great in principle, a little bit difficult in practice. Okay, because you've got this non-differential objective. Okay, so new here is our complexity control. It simply remains to choose the correct value. Okay, so how do we do that? We do it as follows. So here again, I have an example of a data set. So the blue dots are the data set. That's the true underlying pattern. Red is the 10th order polynomial we're fitting, and this is what we do. We apply our trick of, let's play pretend with the out of sample data, yes? It will always matter which order, what initial values you choose. as a starting point, you won't have an idea. You're going to start out at a random coordinate. This is why you do the analysis multiple times. So lots of time for compute. And again, why you're not lazy and do the early stopping bullshit thing. Okay, cool. So we play pretend and we say, let's set aside a validation set. Let's fit the model in sample on the training set, change the value for new as we go, and then monitor the out-of-sample performance, or our proxy for the out-of-sample performance, which is the validation performance, and that's that curve. And what do we see? Fine. In sample, when we have no regularization, so new is very small, in sample performance is great. Out of sample, rubbish, because we're overfitting. Okay, and as we apply the brakes, in sample our performance goes poor. What happens out of sample? We do well. And then at some stage, what's going to happen? We're going to over-constrain, we're going to fit essentially an intercept term. And then what happens to the out of sample performance? It's still rubbish because we've extracted no value. Okay, yes, Shweta.
I was going to say, you said we would be setting the values randomly multiple times. So would that
The
mean
initial values for
the initial values.
when we do the optimization.
So that is our, like from last lecture, our theta vector.
Yes, that's theta rand we're starting off.
So yeah, not the same seed for that
but
same
now
run.
remember, so what your colleague is saying is you're optimizing something. Where you start matters. If this thing has multiple minima to start out with, so this is now the original objective function, surely it matters where you start, which order it's going to be setting them into zero. And it does. So your overruns, you actually might find that they differ. But then if you constrain it far enough, all those objectives are going to look very similar. Okay, and that is the validation analysis. So we need to set up a validation analysis. Okay, almost done, and now I'll give you guys a break. Okay. Now, great. This is easy enough. All we need to do, change the objective function slightly, run the optimization routine multiple times for different values of new, and check how it performs on the validation set. But there's still a problem, right? Right at the beginning, when we set aside the validation and the training set, how did we do that? How would you do that? Come on. I know you've done this. Come on. But just what do what? Come on, tell me. Just random bucket. We take 80% of these, 20% of those. Let's go. Right? That's it. Well, what's to say that that split was good? Right? Okay, so here's the thing. That validation set we set aside, that's a discrete set of observations, right? So this validation curve that we're calculating, this is a function of the data, right? And the data were random, they had noise in them. So this curve is a what? It's a statistic. So when we interview you guys in 2 years' time, when you apply for a job here, and I ask you, what is a statistic? The statistic, that one, yes? Okay. When we interview you and you ask you, what is that? You say, anything that is a function of the data. And is our model a function of the data? Yes, which means what? Which means it's got a distribution attached to it, which means there's some variation. And what is your job as a statistician? Yes, explain the variation, what the uncertainty is, that kind of thing. So there's uncertainty attached to that curve. How do we fix that? Well, we're going to play pretend, but like pros now. Okay. And we set up cross-validation. So indeed, the validation set, optimistic for the out-of-sample error. Okay. Fine. Way to get around this is cross-validation. Cross-validation says, okay, let's create multiple splits. So let's say we were doing 10-fold cross-validation. We had 100 observations. We're going to say, let's take the first 10, set that aside as validation, and use the rest as training. Then use the next 10, set that aside as validation, and so on and so forth. Okay, now, if your data are not ordered when you're doing it in this ordered way. So the data aren't ordered, so you can see how these are corresponding to random observations. Then it doesn't matter that you're taking them in blocks of 10 ordered by the index of the observations. If you're worried about that, you can randomize this and then do the same thing. But essentially, what are we doing? We're trying out different validation sets. Okay, and now what are we doing? We're effectively bootstrapping what? Every time on the validation set we measure something, we get different estimates. So we get like 10 different estimates of the validation error at each point on the curve. So when you look at this curve, at each point on there, we create like 10 different estimates. And then what can we do with those 10 estimates? We can get some idea of the variation. We can calculate the average of those estimates to get the curve. We can calculate its standard deviation to get some idea of its variation. Okay. So we calculate the error over all of the validation sets, and we can calculate some statistics. Okay. And what we end up with is the following. So here's a 10-fold validation analysis applied to that data set. And that's the curve we get. So this is the average, this black line is the average. These bars, the sort of 95% confidence intervals, if you will, around that curve. And now we get an idea of how much variation there is in the validation curve. Remember, this validation curve is the thing that makes the learning part of our machine learning work. If you can't show me this, you haven't shown me anything. Getting an idea of how much it varies, very important, and that's why we use K-fold cross-validation. Okay, fine. How do we use the cross-validation? How do we use this uncertainty? So let's pretend we've got this uncertainty measure for the validation curve. How would we pick a model? Now, if we had just the validation curve, we would go to the minimum, right? Because that's the best out-of-sample performance we saw. But because there's uncertainty about that estimate, what do? We say it could have been as bad as that. It's not implausible that it's as bad as that, so that's one standard deviation up. If we're really conservative, we could go 2 standard deviations up. And then we say, well, let's pick a model, a simpler model on the validation curve, so the actual black curve, which corresponds to that level of uncertainty, and then we read off the regularization parameter from there. So we go to the right, so we're more conservative. And again, so this is now, that step there is applying principle of parsimony. Okay, so we use this variation, go up 1 standard deviation, or 2 if you want to, and then regularize the model at that end. Okay, now just to clarify, in an exam, what I will typically ask you to do is I'll typically just ask you to draw the validation curve. And then you use the minimum or something slightly to the right of that, and you'll be fine. The reason I don't ask you to do the cross-validation is, as you'll see when we do this calculation by hand, or from first principles, it takes a bit of time, and I'm not interested in whether you can do this calculation. I might ask you this calculation in an assignment, but not in an exam. Okay, but do know that this is how you use it. Okay. Now, just a final note on this. This idea that you have uncertainty about this curve is also why I was moaning about whether you should be using more than 1 or 2 regularization mechanisms. Because let's consider the following. Let's say you used 2 regularization mechanisms. So you had one parameter for L1, another parameter for L2. So what's that called? That's elastic net, right? You've seen that before. So now you have to pick 2 hyperparameters, okay? Say nu and a lambda. How are you going to do that? You could brute force, just throw all this shit at the wall, pick some configuration. The problem is, this thing is now a surface, a 2-dimensional surface, and you're going to look at the minimum, and then you're going to go 1 standard deviation up from that. 1 standard deviation up from that, take a surface, like a plane, cut through that surface, and what will you see? You'll see a whole contour of models which are completely indistinguishable from each other. So why bother? Because for that whole contour, you're going to be running the computation. Okay. Cool. So I'll leave that for them as is for now.